so there's just two more sections that we need to discuss. 10.3 is about polar coordinates. Now, I suspect you've probably seen polar coordinates before, either in like pre-calculus or trigonometry or sometime in high school. But high school was a long time ago, so of course we're going to review that a bit. So, the idea is this. Well, actually, you know what? Let's not put these labels on it. So, throughout life, if you wanted to describe a point in the two-dimensional plane, like say right here, then you would just take its distance from two axes, and then if it was to the left of if it was to the right of the y-axis, then it would be positive x-coordinate. If it was to the left of the y-axis, it would be negative x-coordinate. If it was above the x-axis, it would be positive y-coordinate. If it was below the x-axis, it would be negative y-coordinate. In any case, you took the distance between the point and two particular lines, two perpendicular lines called the x and y axes. Now, those distances would be, the absolute values of the x and y coordinates. All right, so that's certainly one way of describing a point in a plane, and that's called the Cartesian coordinate system. There's another way. If we desired, if it would be convenient for us, we could instead draw a line segment from the origin to whatever point we're trying to discuss, take the distance between the origin and that point, which is the length of that line segment, which we'll call r, and then just give the direction in which this line segment goes. The way that you describe this direction is you just give the angle between the line segment and the positive x-axis. Okay? So in this way, we would call the point xy in Cartesian coordinates but in this new scheme, we're just going to give the information r and theta. To describe the point. And that system of describing a point based on r and theta is called the polar coordinate system. Okay? Now, as you might notice from the diagram, x is r cosine theta, and y is r sine theta. So that gives a pretty efficient way to go from polar coordinates to Cartesian coordinates. Going from Cartesian coordinates to polar coordinates is a bit trickier. First thing we can do is we can say x squared plus y squared is equal to r cosine theta squared plus r sine theta squared, which is r squared cosine squared theta plus r squared sine squared theta. Now we can factor out that r squared and just get r squared times cosine squared theta plus sine squared theta. But of course, cosine squared theta plus sine squared theta is just 1. So this actually always turns out to just be r squared. So x squared plus y squared always equals r squared. Okay, good. Now, how do you figure out theta? That's a little bit harder. You see, first of all, you might notice that if you divide y by x, then you'll get tangent theta equals y over x. But first of all, that doesn't make sense unless x is non-zero. If x is 0, that you can't do that, of course, because you're dividing by 0. And there are other complications as well, because whenever you see tangent theta equals this, you probably want to take the arctangent of both sides, but that's not always going to give you the correct answer. We'll get into all of that. So, of course, let's get started with some examples. Okay. Okay, so this one asks us to find the Cartesian coordinates of the point whose polar coordinates, polar, not polar, polar coordinates are, well, the first one, part A, we're going to say the polar coordinates are 4 pi over 3. So this is the polar representation. We want to find its Cartesian representation. Okay, so we just have to use this. Let's okay, so I guess we'll erase this and then restate a lot of that information. So, 4 pi over 3. 4 pi over 3 is 1/3 pi more than pi. Or, yeah, 1/3 pi more than pi. And 1/3 pi is what we would call 60 degrees. So, that's like in approximately this direction or so. And specifically, we're talking about a distance of 4. Okay, so let's say this is the point. We have 4 units along this line segment, and this angle is 4 pi over 3. Okay, so now you need to figure out the Cartesian coordinates. So, again, we just need to use that x is r cosine theta, and y is r sine theta. So, in this case, x is going to be 4 times the cosine of 4 pi over 3. Okay, cosine of 4 pi over 3, that's going to be negative 1/2. So this just ends up being negative 2. And then y is going to be 4 times the sine of 4 pi over 3. The sine of 4 pi over 3 is negative √3 over 2. And so then this is going to be negative 2√3. Well, at least that matches up, right? We have this thing being on the left of the y-axis and below the x-axis, so both its Cartesian coordinates should be negative, and they are. And yeah, this is all we need. So this turns out to be the point negative 2 √3, in the Cartesian coordinate system. All right, next up. B is going to give us a different point. This one is -2 3 pi over 4 in polar coordinates. Now, immediately you look at that and you're like, what does that even mean? Because isn't the r supposed to be the distance from the origin to the point? How could it be negative? Yeah, I agree. That doesn't make a lot of sense, okay? This is basically just notation for something different. This is notation for 2, 3 pi over 4 plus pi. And this is still polar coordinates. Okay? So what's going on here is we're going to take 3 pi over 4 plus pi. Okay, 3 pi over 4 is approximately like right around here. And then we're going to add pi to it. Well, adding pi puts you exactly on the other side. And then it's going to be a distance of 2 away from the origin, so approximately right there or so. Again, if you want to find the x and y coordinates, you just need to take the cosine and sine. So x is going to be 2 times the cosine of 3 pi over 4 plus pi, which by the way is 7 pi over 4. Cosine of 7 pi over 4 is root 2 over 2, so this is just root 2. Then we have y. This is 2 times the sine of 7 pi over 4. Sine of 7 pi over 4 is negative root 2 over 2, so this is negative root 2. And so in Cartesian coordinates, this can be written as root 2, negative root 2. And I just want to point out, this shows that there is some ambiguity to polar coordinates, right? When you give 2 Cartesian coordinates, you just need to give 2 numbers, and that always specifies just 1 point, right? With polar coordinates, though, you could have 2 different sets of numbers that actually specify the same point. That could happen. And honestly, that shouldn't be that surprising, because when you give an angle, well, there's infinitely many numbers that could correspond to that same angle, right? If I give you an angle like 0, we could say, well, that's the same angle as 2 pi, which is the same angle as 4 pi, which is the same angle as 6 pi, and so on. Also negative 2 pi, negative 4 pi, and so on. So, yes, in polar coordinates, you give 2 numbers that will specify a point, but sometimes the same point can be given by more than one representation. Okay? Let's see here. Oh, wait a second. Oh, made a mistake in my notes. That seems to be happening a lot of these days. Right, so I guess I'll just have to fix that up. Okay. All right, so then last one, part C. This one's going to give us -3, negative pi over 3. And again, this is in polar coordinates. We want to find its Cartesian coordinates. Okay, again, you can rewrite this as just 3, negative pi over 3 plus pi. So let's actually do that. 3, negative pi over 3 plus pi. This is still a polar coordinate representation. And by the way, pi plus negative pi over 3 is 2 pi over 3. Okay? So let's see here. 2 pi over 3 is approximately like this direction right here. And we're going to go out by 3 units from the origin. So something like right there. Just looking at my diagram here, it's horribly accurate in terms of the scale of the different line segments. There's a more accurate description in my notes though. This is about the best I'm going to be able to do with freehanding it. Okay, so then again, we can say in order to find the x and y coordinates, x is just going to be 3 times the cosine of 2 pi over 3. Y is going to be 3 times the sine of 2 pi over 3. Okay. Cosine of 2 pi over 3, that's negative 1/2, so this is negative 3/2. And then sine of 2 pi over 3, that's root 3 over 2. So this is going to be 3 root 3 over 2. And so the Cartesian coordinates are just negative 3/2, 3 root 3 over 2, and that's all we wanted. Okay. All right, so then let's talk about the reverse problem. What if you're given the polar coordinates and the reverse problem is you've been given the Cartesian coordinates and you want to find the polar coordinates. Okay, that's a bit trickier. So let's go through that too. Okay, yeah. Find the polar coordinates. Of the point whose Cartesian coordinates, I don't have enough room to spell out Cartesian, so I'll just write cart. Okay, so this one, root 3 negative 1. And this is the Cartesian coordinates. We desire to find the polar coordinates. Okay? Root 3 negative 1 is like approximately, like over here somewhere. So we just need to figure out the length of that line segment and this angle. If we can do that, those will suffice for polar coordinates. Okay, but it's weird because now we have to sort of do this process in reverse. So we have to say root 3 equals r cosine theta and negative 1 equals r sine theta. And then we have to solve this system of equations for r and theta. So it's a little weird. First thing you ought to do in these cases, though, always, is square the two equations and add them up, because that always gives you r squared. Okay? So when you square root 3, you get 3. When you square negative 1, you get 1. You add these two up, you get 4 equals r squared cosine squared theta plus r squared sine squared theta, which, as we already discussed, just becomes r squared. So 4 equals r squared. Okay? So then, if 4 is r squared, then that means that r is either 2 or it's negative 2. Now, once again, it is okay and possible for us to say that r is negative it's a little weird because that's kind of a roundabout notation for what you're trying to say. It makes more sense to just say r is 2. Okay? You can proceed with this, but let's not. Okay, let's not, at least for this example. So we'll pick r to be 2. Okay, well, that gives us our first coordinate here. And that turns these equations into root 3 equals 2 cosine theta. Negative 1 equals 2 sine theta. Okay, in other words, cosine theta equals root 3 over 2. Sine theta equals negative 1/2. And so now we just need to solve this system of equations. Okay, well, first of all, there are infinitely many solutions. There are infinitely many solutions because there are infinitely many angles that would satisfy these two equations. Like, all you need to do is find one and then add 2 pi to it, and then that gives you another. And then you add 2 pi to that, and then you add 2 pi to that, and so on. But let's just say we're trying to find an angle between 0 and 2 pi, okay? I think that makes the most sense. So cosine theta equals root 3 over 2. Wait a second. How could cosine theta be root 3 over 2? Oh. Wait, no. If we're saying root 3, which is the x-coordinate, is r cosine theta, and that becomes 2 cosine theta, and then negative 1 is the y-coordinate that... Oh, well, yeah, that would be because I stupidly graphed it incorrectly. Okay, so, yeah. Gonna have to put some kind of errata in the description of this video. Yeah, actually, this is root 3 along the x-axis and then negative 1 down. So actually, this should be more like here. Sorry about that. So then if we're finding an angle between 0 and 2 pi, we're trying to find this angle right here. We could also find an angle between 0 and negative 2 pi. That would be fine too. But for right now, let's just say 0 and 2 pi. Right then. So anyway, if cosine theta is root 3 over 2, well, there are exactly 2 angles between 0 and 2 pi that actually do that. One of them is pi over 6. The other one is 11 pi over 6. Okay? Pi over 6 has an x-coordinate of root 3 over 2. 11 pi over 6 has an x-coordinate of root 3 over 2. Okay? So 2 solutions between 0 and 2 pi. And I just want to point out, if you just take the arc cosine of both sides of these, it will only give you this one. That's just how the arc cosine function works. It's not going to give you every angle that can satisfy this equation, because that's impossible. All right, so that takes care of the first equation. Second equation says sine theta equals negative 1/2. There are, again, 2 angles between 0 and 2 pi that do that. One of them is 7 pi over 6. The other one is 11 pi over 6. All right. And by the way, if you take the arc sine of both sides of this equation, you get neither of these. If you take the arc sine of both sides of this equation, it will actually give you negative pi over 6, which, again, is not quite what you wanted here. because that's not between 0 and 2 pi. All right, so obviously, if it's pi over 6, then it can't be one of these two. And if it's 7 pi over 6, then it can't be one of these two. So that means it has to be 11 pi over 6. That's the only solution that satisfies both equations. Okay, so 11 pi over 6 is at least one polar angle that could represent this point. Okay? Now, I'm saying in my notes, and this is true, that there's plenty of other ways to represent this point in polar coordinates. Even if you demand that the radius, even if you demand that r be positive, you can still say that this is 2 negative pi over 6. That's totally fine, because all you're doing there is just taking 11 pi over 6 and subtracting 2 pi from it. Which, if you do that, you get the same angle, geometrically. Although, I appear to have made another mistake in my notes. Right then, gotta get on those. Okay, but anyway, that takes care of this one. Next up we have the point -6, 0 in Cartesian coordinates. Okay, so -6, 0 is somewhere like right here. Now, once again, we can set up the -6 equals r cosine theta, 0 equals r sine theta, and then solve that system of equations. We can do that. But it's far easier in this case to just say this is 6 units away from the origin at an angle of pi. So at least one way to represent this in polar coordinates is just say 6 pi. Right, because this angle right here is 180 degrees, which is pi radians. Okay, and then finally we have -1 over root 3 and -1/3. Okay, so -1 over root 3, -1/3, and this is the Cartesian coordinates. And once again, we're trying to find the polar coordinates. Okay, -1 over root 3, -1/3. That's somewhere in the third quadrant. I don't exactly know where, but it's like, let's see. Root 3 is smaller than 3, so that means 1 over root 3 is larger than 1/3. So I guess somewhere like around right there. And we just need to find out this radius and this angle. Okay, so we'll just say -1 over root 3 equals r cosine theta, and -1/3 equals r sine theta. Okay, once again, square these and then add them together first. That's the easiest first step to take. So if you square these and add them together, you get 1/3 plus 1/9, and this has to be r squared. 1/3 plus 1/9 is the same as 4/9. So 4/9 is r squared, which means r equals 2/3, or r equals negative 2/3. And again, you can use a negative value of r, but it's probably more intuitive to use the positive value. Okay? In any case, this gives us our first coordinate here in polar coordinates, 2/3. And so now all that's left is to figure out the angle. So now these two equations become negative 1 over root 3 equals 2/3 cosine theta, and negative 1 over 3 equals 2/3 sine theta. All right, so you do some algebra here, and this turns into cosine theta equals negative root 3 over 2. And then sine theta equals negative 1/2. Okay, so now cosine theta equals negative root 3 over 2. There's two different angles that do that between 0 and 2 pi. One of them is 5 pi over 6, which is about right here. The other one is 7 pi over 6, which is right here. Of course, we're going to want the one that actually corresponds to the quadrant we want. But, you know, just algebraically, we can think of this as having two solutions. So 5 pi over 6 or 7 pi over 6. Then the other one, sine theta equals negative 1/2. Again, two angles between 0 and 2 pi that do that. One of them is 7 pi over 6. The other one is 11 pi over 6. Well, then the only thing that satisfies both of these equations would be 7 pi over 6, so we're done. Okay. So 7 pi over 6. And those are the polar coordinates. Okay. By the way, I guess just for completeness, we can also do it with the negative value of r. So we can say negative 2/3, and then rather than 7 pi over 6, we're going to have to add pi to that, or subtract pi, which actually gives us the same angle, right? Either way, you're going to get pi over 6. Well, algebraically, you might not get pi over 6, but geometrically, you'll get the angle corresponding to pi over 6. So, yeah, you can go through this whole system of equations thing with negative 2/3 in place of r. If you do that, then cosine theta becomes root 3 over 2. Sine theta equals positive 1/2. And then you're going to say, okay, angles between 0 and 2 pi that do that, there's only going to be pi over 6. And of course, as I said before, there are infinitely many more representations in polar coordinates because you can put anything for the angle as long as it corresponds to the same angle. And you know, if two angles correspond, that happens if and only if their difference is a multiple of 2 pi. Okay. Right, and so I just want to say one more thing. There are many texts, I have difficulty saying that word with my accent, sources that would tell you that, oh, you can just divide these two equations and turn it into tangent theta equals y over x. as long as x is not 0. And that's true, you can. But then they go on to say this means that theta equals arctangent of y over x, which is patently false except under certain conditions. Specifically, theta has to be between negative pi over 2 and pi over 2. If it's not, this will not give you the right answer. So like right here, for instance, if we try to do this thing with a tangent, okay, divide y by x, you get negative 1 over 3 divided by negative 1 over root 3. That comes out to be root 3 over 3, which is the same as 1 over root 3. Okay, so tangent theta equals 1 over root 3. Then you say, okay, what angles satisfy this? And again, there's infinite many solutions. In fact, there's 2 between 0 and 2 pi that do this. But according to these sources, you can just take the arctangent of both sides. So according to these sources, it's perfectly fine to say theta equals arctangent of 1 over root 3. And if you put that into your calculator, let's see here. 1 over root 3, the arctangent that will give you is pi over 6. Which is wrong. Okay, it's right if you're taking r to be negative, but if you're taking r to be positive, that's not right at all. Okay, so you need to be very careful of this. What I would recommend is you solve this in the same way that I solved these ones. You just have to set up the system of equations, solve for r and theta. And the easiest way to get started with that is to square them, add them up, get r squared, and then replace that and then do trigonometry. Okay? Okay, so next up, let's talk about functions defined by polar equations. So in the same way that in Cartesian coordinates you can write like y equals f of x, and then this is going to be a function which is going to give you some kind of graph in the xy plane. Also, you can write r equals f of theta, and then this will also give you some kind of graph, but it'll be weirder. First of all, this one has an easy geometric interpretation, well, not interpretation, but it has an easy geometric test to determine if it's valid or not, which is the vertical line test. If a curve does not pass the vertical line test, it cannot possibly be a function y of x. Whereas this thing right here, r equals f of theta, that one doesn't have to pass a vertical line test at all in order for it to be valid. Okay, so this one is a little bit weird, but you can still do calculus with it. Okay. So the first thing we're going to ask here is, how do you figure out the tangent line to a curve that's defined in this way? So what we're looking for is dy dx. Again, in every context, dy dx, as long as x is the independent variable and y is the dependent variable, this always gives you the slope of the tangent line, okay? So, in our case, well, in our case, y is r sine theta, and x is r cosine theta. So we can use that information to figure out what this would be. This happens to be the derivative with respect to theta of r sine theta divided by derivative with respect to theta of r cosine theta. Now, at first glance, you might think that that doesn't look complicated at all. This is a mistake that I often make with this computation. you might think, this is just going to be r cosine theta, right? It's not. It's not, because r is not constant with respect to theta, right? R is itself dependent on theta, so this is actually a product rule, and so is the denominator too. Okay, so we have the first times the derivative of the second plus the second times the derivative of the first. And then we have, again, first times the derivative of the second plus the second times the derivative of the first. And this formula, although a little bizarre, will always give you the slope of the tangent line to a polar curve. Okay? So let's just do, we'll just do one example. Because ultimately this comes down to the same thing every single time. It's just this formula. The only thing that's really hard about this formula is remembering it. And you don't even have to remember it as long as you can just remember that this is how it gets formed. And that r is not a constant with respect to theta. So, so let's see here. We have an example. Find the slope of the tangent line to r equals, r equals, come on. Sorry, my cat just stepped on my tablet, and apparently it needs to restart now. Okay, we're back. So 2 plus sine of 3 theta. Okay. And let's say at the point theta equals, what is this, pi over 4? Yeah, pi over 4. Okay, so here's how it works. First of all, you take dr d theta, because that will be necessary to compute this whole thing. So, dr d theta, this just happens to be 3 times the cosine of 3 theta. And then you put in everything into this. So, this becomes 2 plus the sine of 3 theta times the cosine of theta plus 3 cosine of 3 theta times the sine of theta. Divide this by negative 2 plus the sine of 3 theta times the sine of theta plus 3 cosine of 3 theta times the cosine of theta. It's a mess, but that's what it is. So then, with this, we just need to put in that theta is pi over 4. And then, first of all, this becomes a lot simpler. Well, not a lot simpler, but somewhat simpler. So dy dx, evaluated when theta equals pi over 4, this ends up being 2 plus the sine of 3 pi over 4 times the cosine of 3 pi over 4 plus 3 times the cosine of 3 pi over 4 times the sine of 3 pi over 4 divided by negative 2 plus the sine of 3 pi over 4 times the sine of pi over 4 plus 3 times the cosine of 3 pi over 4 times, cosine of 3 pi of pi over 4. Okay, so you put all this stuff in. Sine of 3 pi over 4 is root 2 over 2. Cosine of 3 pi over 4 is negative root 2 over 2. Wait a second, hang on. This should be cosine of pi over 4, which is actually positive root 2 over 2. Yes, I made another mistake here. There should be pi over 4, and then I think the rest is correct. Right then, so where were we? So the first becomes 2 plus root 2 over 2 times cosine of pi over 4, that's root 2 over 2, plus 3 cosine of pi over 4, 3 cosine of 3 pi over 4 is negative 3 root 2 over 2. Sine of pi over 4 is root 2 over 2. Divide all of this by negative 2 plus the sine of 3 pi over 4. Sine of 3 pi over 4 is root 2 over 2. Multiply this by the sine of pi over 4, which is root 2 over 2, plus 3 times the cosine of 3 pi over 4, that becomes negative 3 root 2 over 2, and cosine of pi over 4, which is just root 2 over 2. So yeah, that's not fun, but that's all you need to do. It's just putting stuff into a formula, right? And this time it actually is as easy as it sounds, okay? It's not as fun as it might sound, but it's not hard. It's not intellectually intense math, it's just annoying. Anyway, this eventually reduces into 2 minus 3 halves root 2. And that would be the slope of our tangent line, okay? Now, I have a couple of other examples in the notes, and I will allow you to read them at your leisure because this part about finding slopes of tangent lines to polar curves is important theoretically, and I think it will influence how we think about the next section, but it won't be directly tested on the final, is something I recently learned. So at least just the slopes of the tangent line stuff, that's not going to be immediately on the final. But as a good first example of problems that we can do with polar functions, I think it was worth at least mentioning. Okay? In any case, homework is up. Go ahead and get some practice with that.